Welcome to this SAT Algebra review on systems of linear equations. We'll begin with a brief review of the three possible types of solutions to a system of linear equations. Next, we'll work through 7 SAT-style practice problems similar to those you may encounter on the exam. Finally, we'll summarize the most important strategies you should know for solving SAT problems involving systems of equations. Let's start with case 1, where a system has exactly one solution. Graphically, this happens when two lines intersect at a single, unique point. For a system to have exactly one solution, the two lines must have different slopes. Their y-intercepts may be the same or different. Next, let's look at case 2, where a system has no solution. On a graph, this is represented by two parallel lines that never intersect. This occurs when the lines have the same slope but different y-intercepts. Finally, we have case 3, where a system has infinitely many solutions. This happens when both equations represent the same line, so the two graphs lie directly on top of each other. In this case, both the slopes and the y-intercepts are identical. Algebraically, this means the coefficients of the variables and the constant terms in one equation are proportional to the corresponding coefficients and constant term in the other equation. Let's begin our practice examples with a problem which asks to solve for one of the coordinated of solution of a standard system of linear equations. Most efficient and faster way to solve this problem is to access Desmos graphic calculator and quickly graph both equations, then locate the intersection point. Another fast and reliable strategy for SAT questions like this is the elimination method. In particular, eliminate y in this problem. If we multiply the entire first equation by 2, the y terms will become exact opposites. Now we're ready to add the two equations together. When we combine them, the negative 2y and positive 2y cancel each other out. This leaves us with 7x equals 21. Dividing both sides of the equation by 7, we find that x equals 3. In this problem, we're asked to find the value of x from a system of equations that contains fractional coefficients. Whenever fractions appear in a system of equations, the first step is to eliminate them by multiply each equation with the least common multiple of the denominators. This makes the rest of the algebra much simpler and reduces the chance of making arithmetic mistakes. For the first equation, the least common multiple of the denominators 2 and 3 is 6. For the second equation, the least common multiple of 4 and 3 is 12. Now that the fractions are gone, we have a much cleaner system to work with. Next, subtract the first equation from the second. Since both equations contain 3x, those terms cancel immediately. This leaves us with 10y equals 60 or y equals 6. Finally, substitute y equals 6 back into one of the simplified equations. Then solve for x. We find that x equals 12. Another option on the digital SAT is to use Desmos calculator. After clearing the fractions, you can graph the two simplified equations and find their point of intersection. In this problem, we need to determine the value of k that makes the system of equations below have no solution. A system has no solution when the two lines are parallel. That means they must have the same slope but different y-intercepts. To compare the slopes, let's rewrite both equations in slope-intercept form. Starting with the first equation, isolate the y term by subtracting 2x on both sides of the equation, then divide by -5. Now let's rewrite the second equation. Isolate the y term by subtracting 4x on both sides of the equation, then divide both sides by k. Since the system must have no solution, the slopes must be equal. By cross-multiply to eliminate the fractions, then solving for k, we get that k equals -10. Notice that the y-intercepts are still different, so the two lines remain parallel and never intersect. Therefore, the system has no solution, making k equals -10 the correct answer. Now, in this problem we need to find the sum of the missing coefficient a and coefficient b given that the system of equations has infinitely many solutions. For a system to have infinitely many solutions, the two equations must represent the exact same line, meaning they have the same slope and the same y-intercept. Like we did in previous example, let's convert both equations to slope-intercept form. Starting with equation 1, we isolate y by subtracting 5x on both sides of the equation, then divide each term of the equation by -2. Now let's do the same for equation 2. Again, we isolate y by subtracting x on both sides of the equation, then dividing by b each term of the equation. Since the lines are identical, their intercepts must be equal. We set the two constant terms equal to each other to solve for b. By cross-multiplying we find that b is equal to -4. Next, we set their slopes equal to each other. Substituting the value of b into this equation, then solve for a, we find that a is equal to 10. Since the question asks for the sum of a and b, we add our two values together to obtain a plus b equals 6. In this problem, we are given a system of linear equations with exactly one solution, and we need to determine which value of is not possible. For a system of linear equations to have exactly one solution, the two lines must intersect at a single point, meaning they must have different slopes. To compare their slopes, we will convert both equations into slope-intercept form. Start with the first equation, subtract x from both sides of the equation, then divide by 2. Similar steps for the second equation. Subtract 3x on both sides, then divide by -6. Since the system must have exactly one solution, the slopes of these two lines must not be equal. Solving for coefficient a, we get that a must not be equal to -1 in order for the given equation to have one solution. This leaves option A to be correct answer. Another common SAT system of equation problem asks to find the value of the expression like x plus y or any other linear combinations from a given system of linear equations. Instead of solving for x and y individually, let's see what happens if we add or subtract the two equations together directly and then simplify like terms. Now we can find the value of the expression x plus y simply by factoring 7 on the left side of the equation, then dividing both sides of the equation by 7. In this last problem, we will translate a word problem into a system of linear equations and solve it step by step. The problem states that a food truck sells salads for $6.5 each and drinks for $2 each. On a certain day, 120 salads and drinks were sold, with a total revenue of $510. How many salads were sold? Let's define our variables to construct the system. We will let S represent the number of salads sold, and D represent the number of drinks sold. Based on the information provided, we can write two equations. Now you can use Desmos to solve this system of equations quickly or use substitution method as it is presented here. Therefore, the food truck sold 60 salads on that day. In conclusion, let's review 5 core strategies for handling systems of equations on the SAT. First, take advantage of the built-in Desmos graphing calculator to find intersection points quickly. Second, use standard algebraic methods, like substitution or elimination, when equations are straightforward to solve by hand. Third, convert equations to slope-intercept form to analyze slopes and intercepts when determining the number of solutions. Fourth, if a problem asks for a combined expression like x plus y, look for opportunities to add or subtract the equations directly. And finally, when dealing with word problems, systematically define your variables to translate descriptive text into clean equations.